then some pneumatics, you know, really old ones that were torn apart. Okay, starting part 2 then, we'll talk a little bit about HVAC controls drawings. You know, when you're in the residential world, it's usually a controls drawing is coming you know, from the factory or the manufacturer along with some appliance or HVAC equipment that you're just installing. In the commercial world, where there's a specific temperature controls contractor who's hired or contracted to do the building-wide controls installation, they might be creating these drawings custom to the control system that they're installing over the top of some other people's equipment. Right? So some manufacturer made the air handler that was purchased and installed on site, and that air handler was shipped without any controls. You know, versus where when you buy a residential furnace, it comes with all its controls. In the commercial world, you have the option. You can say, I want factory controls, or no, we hire a controls contractor who's going to do controls throughout the whole building, custom, you know. And if it's a custom controls package like that, they should be creating schematics that show, in a schematic sense, show the HVAC equipment. Like in this case, this is an HRV, heat recovery ventilator. And then they'll show the locations of all their different controls devices. Usually somewhere, if not on the same page, they'll have a bill of materials that lists out all those controls components and the quantities and model numbers and that kind of thing. And then again, may not be on the same page, but they should write some kind of sequence of operations. And the sequence of operations is usually produced by either the design engineer for the project or the controls contractor, or it's a collaboration between the two parties. This should give you everything you need to know to understand how that system is intended to be operated. You know, what inputs are going to be read into the controller, and then this tells you what logic the controller is going to have to accomplish, and then you can see what outputs go where to different dampers and valves and motors and things like that. But for troubleshooting, whether it's new projects, new construction, or existing systems trying to troubleshoot, it's very important to try to gather as much of this kind of information as you can get your hands on, so that you know, you can walk up to an HVAC system, and this is more true the more complicated they get, and you can observe it operating, and you can start to get a sense of what the current sequence of operation is as you've observed it. But then to try to make an assessment of whether that's the right sequence or the best sequence can be difficult. And you know, you might see it doing something that just doesn't make sense to you, and it doesn't seem like, it's not doing what the last system of that type was doing that you looked at, and you could easily jump to the conclusion that then therefore this is wrong, but you don't always know. I mean, it could be that the engineers knew something that was particularly unique about this system, and that it was very intentional. So if you can go back to these written sequences and controls drawings, you get a better idea of what was intended originally. And then you still might say, well, that's not the best sequence, and then at least you're more educated in making that assessment.
So it might have just been set up as a starting point?
Or just...
didn't have time to get feedback on it?
Yeah, certainly that's one possibility. Another is that you know, a lot of sequences that were written at times when energy wasn't such a concern were different than sequences that we would write now when energy efficiency is more of a concern. You know, it wasn't uncommon in the days when energy wasn't so important. If you just let a system run 24/7, the sequence gets more simple, you know. And sometimes it really does control, but it does work better, but it uses a lot more energy. So you see, I've gone into a lot of buildings where they have some old piece of HVAC equipment, and it has issues, probably controls issues, some mechanical issues. And what the people who operate the building have arrived at is just, you know, it's got issues, but if we just let it run all the time, it does a lot better.
Well, that's any electrical component.
Yeah, actually, it's a very good point.
So we don't turn off our damping machines at night.
Yeah. Okay, so what are sequences of operation, or what kind of information should they convey? So it should be a plain language description of how the system should behave under different scenarios. And you know, they generally come in the format of if this, then that. They're logical statements, right? If this happens, then the following should happen, should follow that. So for example, if the space temperature falls below the set point, that means a call for heat. Then the furnace shall be commanded to fire, and upon the flame sensor proving that the burner is fired, the blower shall energize, right? It's a sequence of events triggered by some change in conditions or some input. They should cover, a well-written sequence of operations should cover all the scenarios that could be expected to occur under normal operation, which includes not just normal operation that is what you want, but also all the possibilities of failure. So it should be, the sequence should specify how the system will operate to protect itself from catastrophic failure or damage in the event of an individual component failure, or logic failure, or extreme circumstances that never were expected, anticipated. So, for example, yeah, exactly. Yeah, other forces in nature. Yeah. So, like actually a really good example of that is on boilers, especially these newer sealed combustion condensing boilers, where they have their combustion air ducted in, usually through a PVC pipe to the boiler, and then they've got their flue gas going out, and the flue gas now is not coming out at 400 degrees like it does in an old, less efficient non-condensing boiler. You can get, frost on, usually you've got a bird screen over your flue at the top, and a bird screen over your combustion air intake, and I've seen both of those frost over. There's a certain amount of moisture in the flue gas, and when it hits that bird screen in really cold Montana winter weather, it starts to create frost on there, starts to ice up, and you don't want to run a boiler if it doesn't have any place for its flue gas to go, and then you also don't want to run it if it can't get combustion air. So the boiler controls need to be able to say, we're starved for combustion air, or got too much pressure in the flue gas discharge, and so I'm going to shut the boiler down until somebody comes and investigates and resets it manually. But here's another example in an air handler that has a hydronic coil, whether it's a heating coil or a cooling coil. In this case, I wrote this as though it was a hot water heating coil. If that fan fails because the motor failed or the belt broke, right? The motor might be spinning, but the fan is not, if the belt broke. If you don't have airflow, actually, how did I read this? Shift close. Yeah. I could have made a better example than that. A better example would have been if, well, no, this is good. This is sound, because, so basically what you do is you write in your sequence so that if the fan is not on, the outside air damper has to go closed. What you're doing is protecting and you should generally have your heating valve go open. So you're trying to protect your coil by keeping water flow through the coil, anytime the fan's not on, especially in a cold climate like this one, if you leave your outside air damper open, there's potential for cold air to still spill into the system because the cold air is more dense, especially if the coil's at a lower elevation than the outside air intake, which they often are. The outside air comes in, falls just because of its density, pools up inside the air handler and freezes the coil. So if the unit is not running, you need to have your outside air damper closed, and typically a heating valve would go open. You can have, and this kind of fits with the cherry, you said cherry switch?
Yeah. Well,
I don't know that brand of switch, but sometimes these damper actuators, especially on an outside air damper, will be installed with a feedback loop so that it can tell the control system whether the damper is open or closed, or an end switch or something. The simplest way is an end switch, which is usually just like not usually a mercury switch anymore, I think, but some kind of gas canister with a little ball in it that can fall to one side and close a contact or whatever, but just based on its position relative to gravity. But to be able to tell the system, hey, I know you tried to close the outside air damper, but it's still open, then go into a frost protection mode. So the sequence should also include all the expected or desired set point and settings values. What do you want your discharge air temp set point to be? What do you want the fan status to be during occupied versus unoccupied? things like that. It also schedules of operation. So is there an occupied mode versus an unoccupied mode, or a day mode versus night mode? And when does the day mode start and when does the day mode end? So this is an example. This is just a blow up of the sequence of operation that was for this HRV. So you can see it. It says provide start, stop, and status functions to the DDC system if the supply exhaust fans should fail. So just saying, tell us what the fan status is. Monitor the fan status with a binary input, and always be aware of reporting, is the fan running or not. To start, or if the supply exhaust fan should fail. Oh, if the supply exhaust fan should fail to start or fail during unit operation, or dampers fail to open, an alarm shall be generated. So this unit actually did have end switches on its dampers. Unit shall be disabled and the outside air and exhaust air dampers shall close if the fan fails. The supply exhaust fan shall run continuously unless overridden by summer or holiday schedules. So you get the idea. It's just telling you how this thing should run based on different scenarios and inputs and whatnot. This section here is unique to HRVs. It says that the discharge air temperature downstream of the heating coil drops below 60 degrees Fahrenheit with the outside air temperature below 32 degrees Fahrenheit. In other words, it's really cold outside. You're doing what you can to keep the discharge air temp above 60, which would be keep it, or maybe this is 50. Anyway, keep it comfortable. If you can't do that, then you need to disable the supply and exhaust fans for 30 minutes and generate an alarm through the system. After the 30-minute delay, enable the fans. In HRVs, the reason that section of that sequence is in there is because in HRVs in this climate, you can start to frost up your heat exchanger. And so one indication is that, if you're getting, especially if you're looking at the leaving exhaust air where there is no heating coil or anything, if that leaving exhaust air starts to get really cold, that's an indication that you have already or will be frosting up your heat exchanger. And so if you can't have some sequence to mitigate that by changing your damper positions or something, depending on the system type, then you might need to shut the system down just to let it thaw out and then start it back up again. Okay, so enough about that. So now let's start talking about efficiency strategies. Any questions before we switch gears into that? I just wanted to give you an overview of the control system stuff, but it's beyond this course. I don't expect you to come away from all that understanding, really a whole lot about the different control system components and types and how it all fits together and how it operates, but just the big picture, like you said, broad brushstrokes kind of perspective. Okay, so what I did here is I just selected I don't know how many are there, 6? Yeah, conveniently like the first half dozen kind of really typical energy conservation measures that I see that are controls related, the ones that I think are maybe the most important ones or the most effective ones, and also the ones that might be easiest to apply in a residential context as well as commercial. So the first one is just to include occupied, unoccupied, or day-night, whatever you want to call it, scheduling. In most cases, we don't need the system to run the same way 24/7. In a lot of commercial buildings, the building is completely empty at night. In your home, you might be there, but you're hopefully sleeping, depending on your own personal lifestyle schedule. But try to get it only running when it's needed to be running, or change the mode. So it might still, like in a commercial setting, the code requires, we talked about this in the last lecture, code requires ventilation when there are people in the building. Okay. You might have an air handler that you need to run all through the night just to maintain certain space conditions of temperature or humidity, but if you know that there aren't any occupants, then you could at least close your outside air damper and take away that ventilation load that we talked about and only deal with the space temperature or humidity load. Okay. And so you would specify an unoccupied period along with a specific unoccupied mode that might be different in the sense that the outside air damper is closed instead of open. Okay. Then you can, once you have the unoccupied or night schedule implemented, then you can start to implement setbacks to your space temperature set points. So if we want to maintain this classroom at 70 degrees during the day when there are people here, maybe we can let it go to 60 degrees at night when there's no one here, and then bring it back up to 70 in the morning. Setbacks can go both ways. Typically in the unoccupied or night period, you'd have separate, like where in the daytime you have one set point, 70 degrees. And then you have a dead band around that set point. So if you get up to 72, you start to cool. If you get down to 68, you start to heat. So that you maintain an average around 70. At night, you don't want it to operate within that dead band. You want it to be off within the dead band. So what you do instead is you have two separate set points. You have a night heating and a night cooling set point. Or the other way around, night heating, night cooling. So if your night cooling set point is 80, you won't cool till the space hits 80. And if the night heating set point is 60, you won't heat till it hits 60. So nothing will happen in between 60 and 80, but if you get up to 80, you'll cool. If you get down to 60, you'll start to heat. And you'll have a dead band around each of those night heating and cooling set points. Demand control ventilation, we'll get a little bit more into this. I'll just list it for now, we'll talk more about it. And then economize your cooling using the cool outside air to cool whenever possible instead of running compressors in an air conditioning system or running a chiller or whatever mechanical cooling system you might have. And then multi or variable speed fans and pumps versus just on-off at constant speed. And hot water supply temperature set point reset. So this is going to be like that discharge air temp reset that I was describing with that pneumatic controller. We'll talk about a different context for that. We'll get into a little more detail on it. And there are many, many more, but as you get beyond this list, you really start to get into ECMs, energy conservation measures, controls-based that really only apply to the more complicated commercial systems. All of these you can apply within a residential system, although economizer cooling and hot water supply temp reset are system dependent. Well, so is multi-speed fans and pumps, I guess. But okay, so the first one, occupied, unoccupied, or day-night scheduling with unoccupied or night setbacks. So the first thing you need is a schedule, and you may have noticed that on your programmable thermostats, like you have purchased for your home, you have options between like a 5-day or a 7-day.
Right. You got to set the weekends, and usually there's like 2 or 3 settings within each day, or
Yeah.
zones. I mean,
Yeah,
serious.
yeah. And so a 5-day, 2-day. People get confused about this, is why I'm bringing it up. A 5-day, 2-day means that you get to have one program for how things run during the 5-day weekday period, and a different program for how things run in the 2-day weekend period. A 7-day says you can make a different program for every day. And so if you had a 7-day programmable thermostat, then you can set, and some of them even then will have within each program, each day, they'll let you have multiple periods. So this is one, this would be kind of at the high end of like flexibility, right? So you can have a different occupied, unoccupied period for each day of the week. And then within each day, you can have like a period 1, which is like everybody's getting up, having breakfast, getting ready for school or work. And then period 2 where everybody's at work, and then period 3 where everybody's come home from school or work and they're having dinner and headed to bed, and then maybe period 4 is like bedtime through the night. And so you have to go in and you specify, for each day, when does period 1 start and stop, when does period 2 start and stop. Pretty straightforward, you get it, right? And then you would say, so basically what you're telling a controller is, maybe I didn't go far enough here, but you would say something like period 1 is occupied, period 2 is unoccupied, right? Or something, right? And then you're going to have your modes, occupied, unoccupied. And so you're going to say in occupied mode, I'm going to heat to 68, cool to 72, and I'm going to have the fan, the unit's going to run in auto mode, which means it'll cool or heat as needed, and then the fan is going to be continuously on. And in the unoccupied mode, I'm going to have it heat to 60, cool to 76. It's on the unit mode, I'm only going to allow it to heat, so if it gets a cooling call, it doesn't get to do anything. And I'm going to have it cycle so that the fan only turns on when there is a call to heat. be clear on these unit modes and fan modes. I think are kind of important. A lot of people don't get this, and a lot of thermostats have these two options. And it's important to be a little bit smart about this, because if you don't need your fan to run continuously, then save some energy by having a fan cycle. But you need to know when you need to have it run continuously. So in commercial buildings where the code does require continuous ventilation via your air handlers, by code you need to have that fan at on, not auto, unless there's some other means of ventilation. For example. So I've gone into a lot of commercial buildings where they have the fan set to auto, so they're only getting ventilation when they get a heating or cooling call. And that doesn't meet the code requirement. It's more energy efficient, but it doesn't meet the code. But in your home, you can set it on auto. Anyway, kind of you get that, the point I'm trying to get across there. So you can do this manually. If you had this kind of thermostat, you can go change the fan mode, the unit mode, and the set points 4 times a day if you want to, every day. Or you can just get a programmable thermostat and then, or a DDC building automation system, and it'll do it all for you. I don't think there's much more to say on it. You guys, you're familiar with this. No? Any questions about it?
Kinda like you're putting down railroad tracks.
And here you can see, this is a screenshot from the front end user interface for a building automation system. This equipment here is what's called a variable air volume terminal unit, or VAV box. And so the information that you can see here, let me just tell you what this thing does first, to get the context. Somewhere upstream of this is a big air handler. Okay, and the air handler feeds air, tempered air, to this inlet, to this box. So the air handler will, let's say it's delivering 65-degree air that has a certain amount of ventilation, outside air, and a certain amount of return air. It's mixed air. Okay, so it's 65 degrees, which is what we call kind of neutral air. It's not really going to heat or cool the space. And the reason it would be, if you're trying to maintain the space at 70, you can dump 65-degree air into a lot of office spaces, and it won't cool because you have enough internal heat gain that does become kind of the neutral point. 65-degree air coming in will hold the space at about 70, which is good. What this does, this variable air volume terminal unit says, if I want cooling, and actually I should have said that a little bit differently. A certain amount of 65-degree air won't cool the space, a minimum amount.
Right.
Okay. So this sends just enough 65-degree air in at all times for ventilation. And then if the space, if the thermostat down here compares current room temp to set point and says it's too warm in here, we need cooling, it opens this damper and brings more 65-degree air into the space to cool it. Conversely, if it looks at the current room temp and says it's cooler than set point, we need heat, it keeps this damper at minimum, and it starts to open this heating valve on this reheat coil that flows hot water, and it raises the discharge temp of the air coming through and heats the space. Okay, so this is a box that, for a room this size, it might be, in footprint, might be half of this, the size of half of this tabletop here, and this deep, and it could be above the drop ceiling somewhere. And I think we probably do have something like this. This might be a constant volume system, I don't know.
Yeah, the heating in this building is all Java locked.
Yeah, I'm sure it is. I would like to see it, actually. I've never had a chance to.
Yeah, we should ask Lance, because he did the week-long certification where they went around and looked at all these.
Oh, nice. And so you can see on this screen, it tells us, here's supply airflow set point. So that's a set point that's being calculated by the controller. So that's coming out of the logic. There's supply air flow rate, which is being measured by the flow station that's installed here. There's supply air damper output, so that's the command to this damper, which it shows it at 12%, so that would be like 1.2 volts probably, if that's a 0 to 10 volt actuator. It's telling us the temperature of the air coming in from the air handler at 67.5 degrees. It's telling us the heating valve is wide open, it's at 100% command. It's telling us the discharge air temperature right now is 103.3 degrees, so it's clearly heating, right? So why is it heating? We can see the zone set point is 72 and the zone temp is 70. So it's 2 degrees under set point, so let's try to bring it back up. We can also see over here are occupied heating, occupied cooling, unoccupied heating, and unoccupied cooling set points. And some system parameters, it says, is the unit enabled? Yes, it is. What's the system mode? It's in auto. What's the occupancy schedule? It's currently occupied. And what is the effective heating set point? So basically, looking at all these programmed individual set points, it says, okay, well, I'm occupied, so that means it's gonna be one of these two set points. And then it also looks at, has anybody made an adjustment at the thermostat, and adjust based on that, tell you what is the actual effective current set point that it's trying to control.
It's pretty ingenious.
Yeah. So with the DEC system, you get quite a bit of information at your workstation interface to be able to troubleshoot. You know, I can go to this and say, well, the space is way under set point, the heating valve's commanded is fully open, but my discharge air temp's only 67 degrees. I'm either not getting hot water to that coil, or the valve isn't actually open, it's stuck, closed, something like that, right? So before I even go out there and start putting hands on or wrenches on the system, I can look at this and get a pretty good idea of what, do I need to bring my wrenches? Right? Go ahead, Brian, you were going to.
No, I was going to say, this enables small, constant adjustments rather than big periodic adjustments.
Yeah, I think, let me make sure I understand your question. By nature, this system is constantly making little tiny adjustments.
Yeah.
Is that what I mean? Yeah. Yeah.
Instead of short cycling, like you have said in the past.
Yeah, it's related. It's a little different. Instead of more like, I guess what I would say is, compared to like some other systems would have more binary, you know, open, close, on, off kind of stuff. Short cycling is a symptom of a problem with binary control, where you say on, off. On, off is okay, but if it's on, off, like on short cycles, that can be a problem. It can also be a problem if it's supposed to go on, off, but it never does. It always is always on. That's the opposite of short cycling. That has more to do with undersized versus oversized equipment. But this system will determine what is the current supply airflow set point. Right now it's at 360 CFM. Okay, that's what, in this case, that's what it's always going to be when there's a heat call, because it only wants that minimum amount of air to come through. So it says, okay, just maintain 306 degrees CFM, or 360 CFM. If the current measured airflow goes above that, the damper will tweak down a little bit, close. If the airflow drops below that, the damper will tweak open a little bit. So we'll try to maintain that as close to that set point as it can. Same thing with the discharge.
Again, small, constant changes.
Yeah, little incremental changes all the time. Yep. Okay. Check the text Smith relay. That's a good time.